Hi, I'm Krishna. So this is our next lab, momentum. So momentum is like energy is the conserved quantity, momentum is also the conserved quantity, right? So momentum is defined as the mass times the velocity. So it's the vector. And we can see that the direction of the velocity. So if you know the direction of the velocity, we can know the direction of the momentum as well. So it's the vector quantity. And it is conserved quantity as well. So in this lab, basically we are going to describe about the nature of the forces when two bodies collides at first, and then we are going to calculate the momentum. We are going to analyzing the collisions, and we are going to calculate the change in momentum at that case. And when two bodies collides, then we are going to measuring the velocities before and after the collisions. So let's go to the first part, nature of the forces when two bodies collides. So, okay, I need this one. Let's say this is my two bodies. This is body A and this is body B. So, this is A and this is B. A is moving in this direction and B is moving in this direction. And when they collide, then the force exerted by, let's say this is FAB. This is FAB is the force A by B. So this is my body A and this is my body B. There are two kinds of forces. One is force exerted on A by B, and another is force exerted on B by A. Okay, when two body collides, then there are two kinds of forces. So if this is body A and this is body A, B, so force on body B by A is FBA, and force on body A by B is FAB. And the FAB in the direction of B and FBA is direction of the A. So we can say that from the Newton's third law of motion, these two kinds of forces are equals in magnitude but opposite in direction. So FAB in the direction of B, FB is in the direction of A. So FAB, these two forces are equal in magnitude but opposite in direction. So these two forces are we call as Newton's third law pair forces. We call FAB and FBA as Newton's third law pair forces. So which are equal in magnitude and opposite in directions. So, and the next thing is that we are going to calculate the momentum. Okay. So let's consider the case of hovercraft. So in our last lab we already captured these motion pictures. So let's say this is the point A and this is the point B. If it is moving from this direction and it's striking in this wall, and then it changes the direction and it goes to the direction B, right? So we are going to calculate the change in momentum at this case. So this is our initial velocity and this is our final velocity. So initial velocity in this directions, this is our V initials, we can call VA, and this is our final velocity, this is VB. So the change in velocity is something like this, VB, and we have to consider the minus V, right? So this goes in this direction, so this goes in this direction. minus v, and this is del v. So the change in velocity is in this direction. So we can say that the momentum change is also in these directions. Change in moment, the direction of the change in momentum is also in the direction of change in velocity directions. So this is how we calculate the change in momentum in our lab. And the third things, okay. But after this, we are going to consider the impulse momentum equation as well. So we can define impulse as force, this is net force, times, okay, the impulse is the net force times the time of that time that exert on how much the net force is exerting, right? So it is also equal to the change in momentum. So this is the vector quantity, so impulse is also the vector quantity. So we can write m del v as well. So this is called impulse momentum equation. So we can see from this equation that when two bodies collide, then F1 and F2 are equal. F1 and F2 are equal in magnitude and opposite in direction, right? So what we can say when two bodies collide about the impulse is that impulse are also equal in magnitude but opposite in direction, because impulse is directly proportional to force, and the force is the vector quantity and time is the scalar. So it's also the vector quantity. So if F1 and F2 are equal, then I1 and I2 are also equal but in magnitude but opposite in direction. Okay, and the next thing we are going to consider about analyzing collisions and calculate the change in momentum. Let's consider the scenario, three scenario. This is the ball. This is moving with velocity v, and this is the target. This is target, and our target is at rest. Let's say this has velocity 0. This is the vector quantity, and we are consider the three kinds of ball. One is, let's say, sticker. Sticker is something like after collision, the ball sticks with the target and they move on the same direction. And the second case is stopper. Stopper is something like after collisions, before collision the ball moves in this direction and target is at rest, right? So after collision, in the case of stopper, the ball actually stops and then the target moves in the right direction. So this is the case of stopper. And then third case is bouncer. Bouncer is the case in which after collision the target moves in right direction and the ball moves in the left direction. So ball actually bounces, right? So this is our target. And this moves in this direction and then this moves in this direction. The ball moves in the opposite direction. So this is the case of bouncer. Now our focus is to calculate the change in momentum in case of sticker, stopper and bouncer. Three kinds of ball. So one of the ball is sticker, which actually sticks after the collisions, and stopper. In the case of stopper, the target moves in the right direction and the ball actually stops there. And the bouncer, the ball moves in the left direction and the target moves in the right direction. Let's calculate change in momentum of sticker, stopper, and bouncer. Three kinds of ball. Okay. So before collision, in the case of sticker, this is sticker, right? Okay. In the case of sticker, before collision, this is the initial velocity. So this is the initial velocity. After collision, the ball sticks with this target and moves in the right direction, right? So it goes in this direction, something like this. This is the B final for the case of sticker. And for the stopper, stopper, initial velocity is same, because all of the case we are considering the initial velocity this and then target is addressed. So initial velocity is same in the case of sticker, stopper, and the bouncer. So stopper, the initial velocity is something like this. And then after collision, the ball actually stops. So this is the final velocity of the ball is 0, right? Target only moves, ball doesn't move. So we are considering the ball, not the target. So stopper, final velocity is 0. In the case of bouncer, this is the initial velocity is same, but the final velocity of the ball is in this direction. This is V initial and this is V final. So we have the final velocity, initial velocity and final velocity of sticker, stopper, and bouncer. So we can calculate the change in velocity, right? So in the case, the change in velocity is V of, let's plot V of, and then minus Vi, right? So del V is V of minus Vi. So V of in this direction and Vi in the opposite direction. So I have to use another chalk in this direction. So V of minus Vi. So the change in velocity is almost 0 in this case. Not actually 0, but a little bit. So something like this. So Vi in this direction, Vi of in this direction, and negative Vi in this direction. So this is the change in velocity. In the case of stopper, del V is something like this is the final velocity, and the initial velocity is minus Vi in this direction. This is V of. So the change in velocity is, this is the change in velocity, right? So in the case of bouncer, okay, in the case of bouncer, this is the velocity V of, and we have to subtract, we have to add the negative velocity V, initial velocity, right? So negative velocity, we have to add the negative velocity. So it goes in this direction, the initial velocity goes in this direction, and the negative initial velocity goes in this direction. So here is the changes. So we can see that change in velocity is maximum at the bouncer, and then the stopper, and then the sticker. So and then we know that change in momentum is something like m times change in velocity. So if the change in velocity is greater, then the momentum change is greater in the case of bouncer, and then the stopper, and then the sticker. So we can say that bouncer has greater change in momentum, and then the stopper, and then the sticker. So let's go to the fourth point, measuring velocities before and after the collision. Okay. I think I can erase this. Momentum, we know that momentum before the collision is equal to momentum after the collision. This is the law of conservation of momentum, right? Momentum So let's say there are two objects, objects A and B. They are moving with velocity VA and VB before the collision, and then after collisions, object. Okay. After the collision, let's say they stick together and they move to the final velocity V in the right directions. So let's write the equation for this. This is for the object A. For the object A, mass of the object is ma and velocity is v, right? Plus mv plus times vb. So this is the total initial momentum, and it is equal to the total final momentum. And the final momentum, the objects A and B are stitched together. We are considering the case something like this A and this is B, and after collisions they both stitch together and they move to the velocity B. So the total mass is ma plus mv, and then total velocity is v, right? Okay, so this is the momentum conservation equation. So we can calculate if you know the initial velocity of the two objects, in this case we can calculate the final velocity of that object after collisions. So this is the case of velocity measure, how we are going to measure the velocity before and after the collisions. Knowing one velocity, we can determine the another velocity as well. So if the case is not something like this, if the case is something like if one of the object stops and another goes to the right direction, then we can consider the object which stops, the velocity equals 0 and the another velocity v, and we can also determine the velocity after collisions. So we can use this kind of equations in this momentum before and after the collision for this case. Okay, thank you guys.